computer and then recompiled at the end. So you don't actually see any speed up over a classical computer yet. But it does demonstrate that these problems can actually be mapped successfully onto this hardware and they can be solved. So now we just really need to scale up the systems to about the level of 200 qubits, and then we should start seeing some speed ups after that. Okay, so I talked about quantum computers for a bit, so now I'm going to talk about the brain and how you might be able to merge the two things together. So, unfortunately, this is a very, very new area of research, so it's a bit speculative. You'll have to excuse me. So adiabatic quantum computing is actually quite well suited to building a quantum neural network, because if you imagine a system of qubits which is just coupled together like this in the same way that the adiabatic quantum computer was, you can imagine that you can represent individual neurons by this system, and then it can find correct weightings between the neurons to be useful for solving problems. So I'll just demonstrate this with this cartoon. So usually with a neural net, you start off with something completely randomized and you give it some training data. And what happens is the neural net starts to learn to recognize objects in the training data, is one example, by changing the connection strengths between the individual elements. And this is in the same way that actual real brains learn, is by changing synaptic weightings in response to input information. So what you do is you keep doing this, and you apply your quantum algorithm at the same time, which allows these connection possibilities to be explored in parallel. So what that means is that the quantum neural network can learn how to recognize training data more quickly than a classical neural network, because it can try out lots of different possibilities of weighting simultaneously. And what this means is that when you give it the test data, it's able to recognize it much more quickly than a classical neural net. So you can kind of see how this might be possible to be realized on one of these types of quantum computing systems. Yeah.
Now, neural networks, one of the biggest problems of this environment for is over and under training. And especially, I don't know what quantum tunneling is, but I did notice on the simulated evening, it took you from one local minimum to the next local minimum, which is the whole idea of undertraining and overtraining. Yeah. Can quantum computers somehow kind of compensate for this problem in your networks?
I think the idea behind the adiabatic model is that if you run the algorithm correctly, it will always find the ground state of the system. So I think the problem is when you've got material like this, I mean, how do you map it finding the ground state of the system onto that being the best thing for recognizing the training data? So I think what you just have to do is you have to actually experiment with this and play around with it to really answer that question. Whether it would be better at undertraining and overtraining, I don't know.
Sounds like a nice research project.
Yeah, I mean, this would be an amazing. This is what the company I mentioned are kind of working on at the moment with their very small systems. So this is an even more exotic and esoteric way of doing it. So this is a bit wacky, but there are certain theories that say that in your quantum mechanical equations you can swap space and time without there being any problems. So one idea that's actually being investigated theoretically is whether you can use a small number of qubits and actually put them through different time steps. And because in quantum computing all the computation is reversible, the qubits can remember all the different steps that they went through, and therefore you can represent these time correlations as a pattern of information. And that pattern of information can just be similar to a spatial or topological collection of neurons. So the idea behind this is that you might be able to use a lower number of quantum neurons and use as a form of data compression to actually represent much more complex neural networks. But this is, like I say, this is extremely new, and it's only being done theoretically at the moment. No one's even tried to think about how you might do it experimentally.
Do all your quantum computers have to be reversible?
that comes from the quantum mechanics, and not all the equations are time-reversible. So the idea is if you can run your quantum computer fast, then you can potentially compute faster than a real brain would run with fewer numbers of neurons. Okay, so this is where it starts to get a bit more sketchy. So the problem with whole brain emulation is basically, can we simulate a human brain with a classical computer? If not, can we simulate it with a quantum computer? And can we simulate it with any type of computer? And what you quickly find when you ask this question is, what is human level intelligence? What is self-awareness, consciousness, and all this? And you get into this very kind of messy area where you start to have problems with zombie arguments, which is, if you can get a digital computer that has all the outward sort of ways of behaving like a human, is it conscious? Do we know if our fellow human beings are conscious? And things like this. No comment. So yeah, again, we have problems with qualia. So this is to do with how we actually, it's things like the redness of red and how we actually visualize things and interpret them inside our own minds. So really the question is, can you equate these two things? And hopefully the next slide will give some different viewpoints. These are actually explained by Roger Penrose in his book Shadows of the Mind. And he puts forward 4 different viewpoints, of which he personally follows viewpoint C. I personally follow viewpoint A. And it would be interesting to know, like, who in the room follows which of these viewpoints, because it's quite interesting. So, well, let me explain them first. Okay. So, yeah, you can discuss. So the first one is what's generally known as the strong AI viewpoint, and it's that all thinking is computation, and we could essentially be simulated and modelled by classical computers. And consciousness would arise as a result of a suitably complex form of a classical computer. Sorry. The second viewpoint is weak AI, which is again ties in with the zombie argument. Is that yes, you could do all this. You could model people as digital brains, but they would never be conscious. So computation in itself cannot evoke self-awareness. C is, in a way, a bit more sensible, I think, than B. This is that consciousness can be represented by physical processes, but we cannot computationally simulate these physical processes. So the way I like to think about this is, using classical physics, we can't simulate the brain, but physical systems, and the brain is a physical system itself. So really the discrepancy is, what I've put in here with our caveat is that with our current computational technologies, we cannot do this.
So hang on, that raises the obvious question of how important quantum processes are.
Yes, it does.
So we're saying any kind of quantum computing falls under the category of our current computational technologies?
No, it doesn't. That's the point I was making. So if we could build a quantum computer, would C then be something reachable?
I don't know that C actually means anything, to be honest with you.
No. Well, so if you require quantum computing, then...
No, but what I'm thinking is...
You can have strong C, which is like the G could never, because whatever physical laws, there just isn't the ability to simulate it.
Well, you're saying that there can be a physical process which is not computable, which is nonsense.
No, it is. We can't efficiently compute quantum energy levels in anything more complicated than a hydrogen atom, so that's not...
I would say A and C are compatible though.
Well, yeah, okay.
Yes, yeah. I think the difference is, well, the difference I see between A and C is, do we need a quantum computer to simulate the brain?
Okay.
Or do we need something that's even more esoteric than a quantum computer that we haven't thought of yet?
Like Alex's quark.
Yeah, like the quark.
When we vote, can we have a 5th category, you know, A, maybe C?
A superposition maybe, yeah.